Welcome to the afternoon plenary. It's a great pleasure to present Professor Sussmann from Rutgers University. Professor Sussmann has his PhD from Kuhan Institute, 1969. He has held positions in Harvard, Chicago, and is presently and for many years at Rutgers. And he has been a visitor to many places, including the Instituto de Matemática. He has been awarded with several prizes, including the Paper of the Year in Control, 97. It's a beautiful paper, 300 years of optimal control. He has held a lot of responsibilities for the community at AMS, at SIAM. He has been a leader for many years for the control community. He has worked for the International Mathematical Union in several committees for prizes. And has been editor of many prestigious journals like the SIAM Journal of Control for many years, Systems of Control, Aplicada Matemática. He has his PhD students count on 2 digits now. He has been invited for many invited talks. I will mention a few. The 2000 talk at the Société Mathématique de France on decision and control meeting. He has talked, invited lecture at the International Mathematical Union Congress in 1978. He has more than 120 papers, 5 books, and so forth and so on. He has worked in several important areas that connect pure and applied math. Just to mention a few: stratifications and real analytic geometry, the algebra of vector fields, nonlinear control, optimal control, and non-smooth versions of the maximum principle, a subject which we will start today and will continue on Friday. So everybody is invited for the continuation of this talk on Friday at the special section on control. We're going to have 2 sections in control, one on Wednesday and another on Friday. So thank you very much, Professor.
Obrigado. Bom, em primeiro lugar, quero agradecer aos organizadores pelo convite, a oportunidade que isso me dá de voltar aqui a essa cidade que eu tanto adoro, desde que eu vim aqui pela primeira vez quando eu era criança, eu acho que já quando eu tinha 11, 12 anos. Mas eu acho que a língua do colóquio é em inglês, né? Então, so let's switch to English, and I'm going to be talking. Can everybody hear? Okay. I'm going to be talking about the issue of how to differentiate in some reasonable sense maps that are not differentiable in the sense that everybody knows. So since Noga alone this morning quoted Henri Poincaré, let me give you a non-quote from Poincaré. Here is one thing that I'm sure Poincaré would not have said, namely that one can scarcely give a satisfactory definition of derivative. Newton, Leibniz, Euler, the Bernoulli brothers, Lagrange, Legendre, all those people could have said that because, as we all know, there was a tremendous lack of clarity about the precise meaning of the notion of derivative when that notion was introduced. And what I want to tell you is that as soon as you start looking for good notions of derivative for functions that are not smooth and that don't have derivatives in the classical sense, a somewhat similar situation arises to that the founders of our field found themselves in. Namely, one knows how to compute things, but it's not clear what the definition behind those things is. So let me give you a couple of examples here. Well, I think everybody will agree that if there is such a thing as the derivative of the function absolute value of x at 0, it should be a set. You may argue that it's just the set consisting of minus 1, 1, or it's the whole closed interval minus 1, 1, but there are certainly two slopes of this function at 0, so whether you like the set of two elements or the whole interval, you should agree with me, I hope, that it's going to be a set. Now, if I give you other examples, it's more or less clear that if you take a function like mod x plus, say, sine 1 over x multiplied by something that's little o of x, like mod x to the 3/2, the derivative of that, whatever it is, it should be the derivative of mod x, because this other part doesn't count because it's little o of x. So the derivative should be the interval minus 1, 1. And I sort of changed my mind. I put in a homework problem and then decided to write down the solution. But the point is that since we don't have a definition, it's part of the rules that you're allowed to cheat and make up your own definition. So homework problem, what's the derivative of x sine 1 over x at 0? Answer, well, let's change a little bit the definition of derivative. And I think this is the kind of change that the founders of our subject would not have thought of, because they weren't used to thinking about sets. But if anyone had the idea and gone and told them, they would have found it very reasonable. So let's define the derivative of a function at x, always functions of one variable so far, to be the usual quotient of increments, except that instead of taking just the quotient, I take the set of all values of the quotient for all values of the increment between 0 and delta, and I take the limit of that set. Limit in the sense of some reasonable notion of convergence of sets. For example, Hausdorff measure, Hausdorff distance. Okay? So, here is a perfectly reasonable definition of derivative that's different from the usual one, as long as you are willing to accept sets. It's plausible, and it gives you the interval minus 1, 1. Okay? So, we have a few examples. And now that we have a few examples, let's examine what this tells us. Well, so one can ask, what are the real mathematical definitions that would give rise to the results of those examples? And so what you see is that we find ourselves in the same situation now as the founders of the subject did, and as our undergraduate freshman calculus students find themselves now. Namely, our students will know that the derivative of x squared is 2x, or that the derivative of sine x is cosine x, but try and ask them what's the definition of derivative. And not that many will be able to produce a correct answer, and quite a few won't even appreciate the point of why one needs such a thing. And of course, the reason that you need such a thing is that you want to have a systematic theory, some kind of calculus, so that if you know that, for instance, the derivative of mod x at 0 is the interval minus 1, 1, and the derivative of mod x to the 3/2 sine 1 over x is 0, then the derivative of the sum is the sum of the derivatives. You want to have a systematic way of computing differentials, applying systematic rules. And it's not that easy. As you will see in a few minutes, the derivative of mod x is minus 1, 1 in the sense of several rigorous theories, like the Clark generalized gradient. But the derivative of the second term in that formula is 0 in the sense of different theories, like the classical differential, but not in the sense of a Clark generalized gradient, for example. So you have one theory that gives you an answer for the first term, another theory that gives you an answer for the second term, and unless you have a theory which includes both, and for which the derivative of the sum is the sum of the derivatives, you cannot really add them. So it's not that simple, but the situation is basically that it's more or less clear what the set value derivative of some maps at least should be, although it's not completely clear. Remember, the set minus 1, 1 versus the interval minus 1, 1, so we still have some things that need to be clarified. And the question is, so we have the problem of how to find a rigorous definition. But of course, there is a big difference between ourselves now and the founders of the subject 300 years ago. Now we really know so much about rigor. We have gone through mathematical logic, Russell, Whitehead, Gödel, Bourbaki, what have you. So we know so much about rigor that our problem is not really that we cannot find a rigorous definition. The problem is we can come up with dozens of them. perfectly rigorous and different, non-equivalent. They give different results. So the question is not so much how to come up with a rigorous definition, but how to choose one that will have reasonable properties. Okay? And, or, if there are dozens of different theories of generalized derivatives, then maybe we'll go one step higher in abstraction and give a general axiomatic definition of what one means by a theory of generalized derivatives, and then there are lots of them. Okay, so this is the situation, and going back to the example I discussed before, I had proposed, let me leave it here. I had mentioned that there was this definition of derivative, which is a plausible alternative to the one everybody knows, in which you take the set of all values of delta y, delta x, for delta x in the little delta neighborhood of 0, and then you take the limit of that set. Another possibility would be to do the same thing, but first take the closed convex hull of the set of all values. A third possibility, or fourth possibility, which would make sense particularly for functions which are classically differentiable in lots of places, for example, Lipschitz functions that are differentiable almost everywhere, is you take the set of all values of the derivative at the points where it exists on the interval, on the delta interval, and then take the limit of that set as delta goes to 0. A fourth possibility would be to do the same thing, but taking the closed convex hull first. And if you look at this type of thing for a minute, it's rather trivial to see that for the examples I have given you, these four choices don't usually give you the same answer. And in fact, for absolute value of x, 1 and 3 will give you the set minus 1, 1. And 2 and 4 will give you the interval minus 1, 1. Because you are taking the convex hull in 2 and 4. For the other function, x plus absolute value of x to the 3/2 sine 1 over x, 1 will give you the set minus 1, 1, 2 will give you the interval minus 1, 1, and 3 and 4 will give a horrible answer, namely everything. Because the function x to the 3/2 sine 1 over x, the derivative oscillates between higher and higher upper and lower bounds as you approach 0. So some of these answers are good and some of these are bad. Why the first good in here? Well, because you want the classical theorem that says that when a function has a minimum and the gradient exists, the gradient is 0. In the set-valued setting, it's going to say that when a function has a minimum, then the gradient belongs to the derivative. And then 0 belongs to the derivative. And that will be true for this set, but not for this one. So this is one reason why 2 and 4 give a good answer for absolute value of x, but 1 and 3 don't. So the question is, what should the theory be? And before I get into that, let me mention that there is something called non-smooth analysis, which has been in vogue for many years, and this stressed the Clark generalized Jacobian, which is essentially the vector-valued version of what I was calling 4. That is, you take the derivatives of all the places where the derivative exists, you form, say, for all points in a delta neighborhood of the point you're interested in, you take the closed convex hull of that and you take the limit as delta approaches 0. And then, of course, this is an interesting notion, but it has some drawbacks. One of them is that you don't have a good chain rule. It's not true. By the way, I forgot, maybe I should have said this before. So this is the definition that I was talking about. You take the set of all values of the classical derivative at the points where it exists in the delta neighborhood. You take the limit of that, you take the closed convex hull of that, and you take the limit as delta goes to 0. So this is the Clark generalized Jacobian. Now, the Clark generalized Jacobian, as I was saying, has has a number of drawbacks. One of them is that the chain rule doesn't hold. It holds with a convex hull, but that's not very good for reasons that I hope will become clear in a little while. In many cases, the Clark generalized Jacobian has an unreasonable value. For example, for this function over there, it's the interval minus 6, 6, whereas it really ought to be minus 1, 1, because the second term is little o of x, so it shouldn't contribute anything. And for other functions that are not Lipschitz, it doesn't exist. And even when a function is both Lipschitz and differentiable at one point, it's not necessarily true that the singleton of the differential is the Clark generalized Jacobian. The Clark generalized Jacobian can be much bigger. So there are all kinds of reasons why one has to look for other possibilities. Now, it seems to me that with my limited knowledge of history, that historically what happened is that this idea of the Clark generalized Jacobian, which when you are talking about scalar functions, it's called the Clark generalized gradient, it arose from convex analysis, because for convex functions it's natural to look at the subdifferential, and it turns out that the subdifferential, in that case, you can rewrite the definition of the subdifferential of a convex function at a point in a way that doesn't mention convexity, and it just requires the function to be Lipschitz near the point, which convex functions are. So, and then since you can rephrase the definition of the subdifferential in a way that makes sense for general Lipschitz continuous maps, it was natural to think that maybe this was the notion to use, but there are many reasons for not using that. So now, in this talk, I want to focus on vector extensions of the first idea. Remember, that was that you take all the increment quotients in some interval around the point, and you take the set of all those, and you take the limit of that, or the limit of the convex hull. I want to focus on extensions of this idea, and then, of course, one of the problems is that it's not clear at all what you mean by delta y over delta x when x and y are vector valued functions. So that has to be taken care of. Gee, it's hard to control that. Wow. I'm supposed to be a control theorist, so I should know how to do this thing. Okay. And again, we have the problem that it's not clear whether the right choice is 1 or 2. And as I hope I will convince you that once you go to a vector valued case, the right choice is neither. It's somewhere in between. You see, in one dimension, there are lots of things that you fail to see. I mean, if a set is connected, then it's convex, and you don't have notions in between connectedness and convexity. So it's very, very difficult to see certain distinctions, but in higher dimensions, these distinctions are going to become crucial. So, to conclude this introduction, let me point out that there are lots of definitions of generalized derivatives that various people have proposed. So lots of people, and I myself plead guilty to proposing at least 4 of them. And there are many more, and of course, as you can imagine, once we get to this point, people are beginning to run out of good names for these things. So you start getting all kinds of weird quasi, pseudo, S differentials and things like that. But the crucial point, of course, is that one needs some kind of motivation, because, of course, as long as you don't know what you want it for, you can define the derivative in any way you like, and it doesn't make any difference. And here, the specific motivation that I'm going to focus on, because it's a part of a program that I have been involved in for many years, is to have the kind of notion of generalized derivative that's appropriate for proving general versions of the Pontryagin maximum principle, non-smooth, very non-smooth. And in order to do that, the basic ingredients are two. You need a notion of differential that has a good open mapping property. What that means in the setting of a classical differential is what that should mean in general in the setting of a set-value differential is that if you have a derivative, which is going to be a set of linear maps in principle, and all these linear maps are surjective, then the map F itself maps neighborhoods of the point to neighborhoods of the image. This would be the open mapping theorem. In the case when the derivative is just a single linear map and it's the classical derivative, this is under, you have to be precise, and I will be in a little while. If F is continuous in a neighborhood of a point and differentiable at a point, and the differential is surjective, then F itself maps neighborhoods of the point to neighborhoods of the image. And in the set-valued setting, this is the analog that we want. And notice that for an open mapping property to be useful, it's good that the set of these sets, derivative sets, not be too big, because the bigger your set lambda is, the more conditions you have to verify. The larger the set of lambdas of members of lambda that have to be surjective. So theories with a derivative that's too big are in principle not good, but on the other hand, it cannot be too small either. For example, if you are going to have the open mapping property, then when a map is not open at the point, then the differential had better contain at least one non-surjective linear map, because otherwise you would be violating the open mapping property. So we need theories with some open mapping property. And notice that the special case of the open mapping theorem, the open mapping property, is the theorem for the classical differential, that if a function has a local maximum or minimum at a point, then the gradient is 0. Now that's, of course, because if the gradient wasn't 0, it would map neighborhoods of the point to neighborhoods of the image, so it wouldn't have a minimum or a maximum. So that's fairly trivial. Okay. So, and then, so this is one requirement. It should be a theory that has a good open mapping property. And the other one is that we should be able to differentiate lots of flows of vector fields. In particular, vector fields that are not C1, and perhaps even vector fields that are not Lipschitz, okay? So, that's what we want. Now, and as I said, I am going to be focusing on this, so this does not exclude the possibility that for other purposes there are other notions of generalized derivative that are extremely useful and convenient. So I don't want to make any absolute claim that one particular, that what I am going to propose here is the only thing you can possibly do. Now, briefly, let me skip some unnecessary things here, because I'm sure everybody has heard the words category and functor, and if you haven't, it doesn't matter, but I mean, roughly speaking, a category consists of having some objects and some morphisms, like, for instance, linear spaces and linear maps, topological spaces and continuous maps, smooth manifolds and smooth maps, or you could have smooth manifolds and continuous maps, or you could have smooth manifolds with a distinguished point and smooth maps that preserve the distinguished point, and all kinds of millions of different things, okay? So, and a functor is a correspondence that assigns to each object in one category an object of another category, and to each morphism another morphism, so that the obvious property such that the F of the composite is the composite of the F's whole, okay? So, for example, well, one obvious example that we are going to need in a minute, if you consider the category of C1 manifolds with a distinguished point and smooth maps, C1 maps that preserve the distinguished point, then for each C1 manifold with a distinguished point, you have a linear space, the tangent space at the point. And for each map that maps the distinguished point to the distinguished point of the second object, you have the differential which is the linear map between the tangent spaces. So the classical differential of C1 maps is a functor from the category of C1 manifolds with a distinguished point and base point preserving maps to the category of linear, finite dimensional linear spaces and linear maps. And it turns out to be convenient, since in any case I'm doing set-valued analysis, to talk about set-valued functors. Let's call them multifunctors. So that's like an ordinary functor, except that f of a morphism can be a set rather than a single thing. For example, the differential of a map could be not a linear map, but a set of linear maps. Or in fact, it will turn out to be a set of sets of linear maps. Okay? So the specific question I'm interested in is then the following. We want to extend this, the theory of the classical differential of C1 maps to a theory that's defined on a class of objects that's larger and a class of morphisms that are larger. And in particular, what I want to do is I want to differentiate lots of maps that are not C1 or even differentiable in the classical sense. And by analogy with the examples I gave you, these generalized differentials, it's very common in most of the theories that exist, but not all of them, that the specific kind of object that the generalized differential of a map at a point is the set of linear maps, where the classical differential would be a single linear map. The generalized differential is going to be a compact, non-empty set of linear maps, and it's not going to be unique. This is unfortunate but important. And so the idea would be that if mu is a map with specifying a base point in the domain and a base point in the range, and so then f of mu would be the differential of that map, what that will mean is a set of compact sets of linear maps between the tangent spaces, and the composition property will say that if you take a differential and compose it with another differential, the result is a differential of the composite, but not the other way around. The typical example is if you have a Lipschitz function, say, with a corner at 0, so the differential is going to be big, and then you compose that with its compositional inverse. The composite is going to be the identity map, because differential consists of just one object, and you're not going to get that by composing two sets. So the composite of these two sets is going to be a differential of the composite, but not every differential of the composite will arise by composing differentials. Okay? Now, let me skip details. So modulo technicalities, the precise definition, and this is what I had in mind when I said let's give an axiomatic definition so that we can start characterizing things, comparing different theories. Forget about the word non-directional for the moment. Generalized differentiation theory will mean that I take the category of pointed manifolds of class C1 with set-valued maps. That is, the objects are manifolds of class C1 with a distinguished point, and the maps are set-valued maps. I want to be able to differentiate set-valued maps. To the category, this means finite dimensional real linear spaces, and the closure is because the morphisms are not linear maps, but compact non-empty sets of linear maps. Okay? And you want the product rule. And the product rule is, I hope are there any undergraduate students? Because the product rule says that the differential of a product is the product of the differentials, and we all know that one shouldn't say that, and if a student of mine says that, that student flunks the course. But if by product you mean Cartesian product, it's true. And that's what's meant here. Okay? If you have a map from F1 from M1 to N1 and F2 from M2 to N2, and you take the Cartesian product, which is a map from M1 cross M2 to N1 cross M2, and at a point in the product, the differential there is the product of the differentials. Okay. So, I'm not saying that you should remember and analyze in detail this definition. All I'm saying it's a very simple definition. Multifunctor means essentially that you have the chain rule. A composite of derivatives is the derivative of the composite. Extension of DC1 means that you take the classical differentials of C1 functions and you extend that. So you should your theory should give you for a C1 map the differential that you know. And local is the obvious thing. The differential at the point depends on the map in the neighborhood of the point. Okay, so what I want you to retain from this transparency is only that the definition is very simple. It doesn't matter exactly what it is. And what I would like to do now is go right away to one example of a theory that has turned out to be surprisingly useful because of the ratio power of the theory over simplicity. It's extreme, power, it's very powerful, but, okay, so time simplicity. I mean, not quotient. Now, it's very simple and also very powerful. And these two things together, I think, make it worth looking at. What I mean by simple, you'll see by looking at the definition. And what I mean by powerful is that with this theory, you can go beyond almost all existing non-smooth versions of the Pontryagin maximum principle just by applying this theory. And you can prove results that go beyond the results that people working with non-smooth analysis and following essentially the Clark generalized Jacobian approach were able to prove by other methods. So this is extremely strong. And in order to tell you what the theory is, I have to get technical for a minute, because the fundamental thing, as you will see, is that we want to have a theory in which we are dealing with certain set-valued maps, and we want to have a theory in which you have good fixed point theorems, because ultimately when you get technical, the proofs depend on some fixed point theorems. And for people who are familiar with fixed point theorems, set-valued extensions of the Brouwer fixed point theorem, of course, the natural idea will be that we want to have a theory in which you can use the Kakutani fixed point theorem, because that's the obvious theorem. But exactly as I told you before, in the one variable case, having a disconnected set of values such as -1, 1 is not good enough. And on the other hand, having a convex set of values is too much, and you need something in between. It will turn out here that we need something much weaker than maps that satisfy the conditions of the Kakutani fixed point theorem, but for which you still have good fixed point theorems without having convex values necessarily. And that's why I want to introduce this notion that has also appeared in the literature in other contexts. For instance, there is a paper by Haddad several years ago that calls it C0 approximable. So let me define a set-valued map. This double arrow is my own notation for set-valued map. A set-valued map is between metric spaces is regular if for every compact subset of the domain, two things happen. First of all, the graph of the piece of the map over that set is compact. Now, this condition 1, if the map was single-valued, this is just continuity. This is exactly what being continuous. This is equivalent to being continuous. And the reason that I want to have a notion like this in the set-valued case is that we want a natural set-valued generalization of continuity, because, of course, the Brouwer fixed point theorem doesn't say that every map from the unit ball to itself has a fixed point. It's got to be continuous. In the set-valued case, we need something like that. Okay? And the second point is that there is a sequence. So the second condition is that it should be approximable in some sense by single-valued continuous maps. And the sense of the approximation, I learned after I wrote this transparency, that this is called upper Vietoris convergence. And Vietoris is known, I'm sure, to you for at least two things. Number one, for the Mayer-Vietoris sequence and second because he died last year at the age of 111. So this, okay. What this says is that given any neighborhood of the graph of the limit, the graph of the FJs should eventually be inside that neighborhood. This is Appier-Gutierrez convergence. If you want a nice example of this type of convergence, suppose you have a function like, okay. Suppose you have this function, okay? So this is the x-axis, 0 here and 1 here, okay? Suppose you have this function. And suppose you look at the partial sums of its Fourier series. What does that converge to? If you draw the picture, you'll see that as you approach, okay, there is some, it is sort of converges to the function that's like this, but there is a little tail. So what this function really converges to this set-valued function, okay? With this little tail, this is the so-called Gibbs phenomenon here. Gibbs. Can you read backwards? Okay. Gibbs. This is the, okay. So, you see, because if you take this thing with the tails, but certainly not if you don't include the tails, if you take that thing with the tails, given any neighborhood of this graph, the graph of the kth partial sum is inside that neighborhood for k sufficiently large. Okay, so that's an example of the kind of convergence. And notice, to give an even simpler example, when you have a function, oh, here, this is going to be a disaster. If you have a function like this, a set-valued function like this, 0, 1, and in here it's the whole interval 0, 1, you can easily approximate it by single-valued continuous functions in the sense that I defined. But if you take just these 2 points here, but not the segment in between, there is no way on earth that you're going to be able to approximate it by single-valued continuous functions. So this appears to suggest that when you can approximate by single-valued continuous functions, somehow the values should be convex. That's far from being true. But it cannot be anything. For instance, you cannot have a situation like this without the segment, the vertical segment in the graph. Okay? And again, now if you go back, those who are familiar with the proof of the Kakutani fixed point theorem, 99% of the proof amounts to proving that the map, say from the unit ball to itself, a set-valued map with compact graph and non-empty convex values, is regular in the sense of this definition. That is approximable in this very specific sense by single-valued continuous maps. The remaining 1% is that once you have the approximating single-valued maps, you apply the Brouwer fixed point theorem and you get a fixed point for each of these maps, and then you take the limit, which this particular notion of convergence allows you to do. But that's the trivial part. So the hard part is proving that the map that satisfies the hypothesis of the Kakutani theorem, convex graph and compact graph and non-empty convex values, is approximable by continuous functions. But notice that the Kakutani fixed point theorem is not really such a good theorem because, for example, it has a conclusion that's clearly invariant if you conjugate by a homeomorphism of your space. Certainly, if a map has a fixed point, you conjugate by homomorphism. You still have a map with a fixed point, but when you do something like that, you lose the condition that the values are convex. So, what one needs is a theory where you can do the Kakutani fixed point theorem and where, in addition, you have some reasonable invariance under various nonlinear operations. And, for example, if you go back to this definition of regular maps, it's fairly trivial to see that the composite of two regular maps is regular. That's easy. In particular, if you compose a regular map with a continuous map in the domain and another one in the range, you still get a regular map. And in particular, if you have a map from a space to itself and conjugate by a homomorphism, you still get a regular map. So this is a theory that has much better invariance properties than the theory of maps with convex values. Set value maps with convex values. Now, what is the point of giving this definition? Well, first of all, you have the obvious fixed point theorem, which says that if you have a non-empty compact convex subset of a normed space and a regular map from that set to itself, then it has a fixed point. This is, if you want, the infinite dimensional version of the analog for regular maps of the so-called Key-Fan-Glicksberg infinite dimensional Kakutani fixed point theorem. And I would like to show you how using this notion of map, which is the analog of set-valued map, which is the analog, the set-valued analog of what for single-valued maps would be just plain continuity, you can get a notion of derivative that's extremely simple and very powerful. So let me tell you, here is the definition. Suppose you have a map from Rm to Rn, set-valued map, not necessarily single value, and I want to define what I mean, what it's going to mean for a compact set of linear maps to be a derivative in this generalized sense. This is the generalized differential quotient of the map f at 0, 0. Here is what I mean. I say that the set lambda is a generalized quotient, a generalized differential quotient of f at 0, 0. If, well, forget about the irrelevant epsilons and deltas that one always has to put in things like this, but the crucial thing is that, roughly speaking, you have a set-valued map with values matrices, which is regular, and essentially takes values in lambda. Actually, you have to say in a neighborhood of lambda, but that's not very important. And suppose f was single valued, okay, just to make it simpler. If it's single valued, when you have a map that's everywhere defined and its graph is contained in another one, which is also a single valued map, inclusion means equality. So the only way, if this is already defined for all x, the only way the graph of this one can be larger is if at some point in the graph of this one you have another point with the same x coordinate, because if otherwise this wouldn't mean equality. So essentially, what am I saying here? Think of the single valued case. Think of f of x as our friend y, and if we are working near 0 and f of 0 is 0, f of x, think of x as delta x and f of y as delta y. I'm saying that delta y should be g of delta x times delta x. So this is a kind of analog of saying that g is a kind of delta y over delta x. But I'm saying allow g to be set valued. But of course, in the case where f is single valued, the set value, for instance, takes the very extreme case when x is scalar. Then if f is single valued, when x is different from 0, g of x cannot have more than one value. On the other hand, of course, if f is set valued, g of x can have more than one value. But, okay? So, just to give you a completely trivial example, for instance, suppose f of x was our good old friend mod x, what can g of x be? G of x can be this function with value minus 1, 1. And then, of course, if this is g of x, f of x is equal to g of x times x. So you have the factorization. So, and g of x essentially takes values in the set, well, actually, exactly in this case, you don't even need the delta, takes values in the interval minus 1, 1. So that makes the interval minus 1, 1 qualify as a derivative of this function at 0, as I said before. Now, Second observation, suppose you wanted just the set with minus 1, 1. There is no way. You could, of course, you also have a factorization with equality here. If instead of the whole interval minus 1, 1, at 0, you put just the set consisting of minus 1 and 1. You still have the same factorization. But then the resulting G will not be regular, because you won't be able to approximate it by single-valued continuous maps. It turns out that if you look at this a little bit carefully, this will, of course, a special case will be when G of x has a compact graph in some compact neighborhood of 0 and convex non-empty values, right? But it turns out that the values of G, and in particular the set lambda, which is roughly speaking G of 0, although it's better to say it this way, the set lambda, it cannot be any set, but it doesn't have to be convex. And this allows for a tremendous amount of flexibility in the theory. And now, just to tell you what is happening without giving any details, let me, I missed, okay. Number one, the chain rule is trivial. And again, I won't do the proof or anything, especially if I'm telling you that it's trivial. You go home and you can do it in 1 second. But let me just point out that even for single-valued functions of there is a fairly simple paper, but rather remarkable, by Botzko and Grosser, that says that if you have a function, if you have a continuous function f from Rn to Rm that sends 0 to 0, for f to be differentiable at 0 with differential L is exactly equivalent to f admitting a factorization like this, where G is a matrix-valued function which is continuous and such that G of 0 is the derivative. And the remarkable thing about this little pedagogical observation, it's not a coincidence that the Botzko-Grosser paper appeared in the American Mathematical Monthly. The point of this observation is that this is a way of characterizing differentiability in which there are no error terms. They are absorbed into G. And so this gives you the most trivial conceivable proof of the chain rule, where you don't need any epsilons and deltas. Now, with exactly the same argument, I won't give you the details, but the chain rule for these generalized derivatives is completely trivial. And let me give you one more example. Once you have the chain rule, then they make sense intrinsically on manifolds, because you just take coordinates, you define it via coordinates, and then when you change coordinates, the chain rule will tell you that the thing transforms the way we want. But now, let me give you the most important thing, that the open mapping theorem is so trivial that you can even fit it into two transparencies in such a way that you can put the transparencies here in this limited size projector, and you can still see the whole thing together. So this transparency together with this transparency, and you don't even need, I had enough room in the transparency to put other stuff in there. Okay. These two transparencies together, that's the proof of the open mapping theorem. And again, without going into details, let me tell you what the crucial point is. The crucial point is that if you want to find y in f of x, that is, you want to show that the image of f contains lots of points, which is the kind of thing you want to show in the open mapping theorem, it suffices to find y in g of x, x, because g of x, x is inside y. And if g of x is onto, then it has a right inverse in various ways. For example, I even want one that will depend continuously on the matrix. So take the Moore-Penrose pseudo-inverse. So that means this thing composed with this is the identity map. So solving this, you will solve this if you manage to solve this. And once you see that solving this will prove that y is in the image, this is a fixed point condition. For map x to this thing, x goes to this thing. For fixed y, that's a map. You find a fixed point, and that gives you your solution. So, but notice, and this goes back to the remark I was making before, you are applying a fixed point theorem. In this case, it would be the fixed point to real, for regular maps. You are applying it for a set-valued map, which is not the original set-valued map G. It's the original set-valued map G, which you are assuming takes values in the space of surjective linear maps. It's the original map G composed with the map that assigns to each matrix, to each surjective map, its Moore-Penrose pseudo-inverse. And that map is certainly nonlinear, and therefore if you had started with a G that has convex values, the map that you get here and to which you apply the fixed point theorem is not a map with convex values, so you wouldn't be able to apply the Kakutani fixed point theorem, and that's why you need this condition. You need this more general theory. This is what I was alluding to before when I said that you need a theory in which you can have set-valued maps that have fixed points, good fixed point theorems, but you don't want to restrict them so that the values are convex because you want to apply nonlinear operations to them. Okay. So, fine. In any case, those who want to see the details, all this stuff is in, you can look it up in my webpage, so you can read the details there and a lot more that I'm not talking about. I think I have only a few minutes left. How many? 5. Okay, so let me make a few remarks, a few disconnected remarks that some of which I really should have made earlier. Why does one want to differentiate set-valued maps? Well, lots of reasons, but here is a very simple one. If you want to do a Pontryagin maximum principle involving continuous vector fields, and you want to be able to do the analog of the variational equation to differentiate the flow maps, continuous vector fields don't have uniqueness of trajectories. Therefore, the flow maps are set-valued rather than single-valued. So some set-valued maps show up naturally when you are trying to look at flow maps of continuous, not necessarily Lipschitz, continuous vector field. Second, why do those maps in any way fit this theory? Well, if you think for a minute, can take a flow map of a continuous vector field, and therefore a flow map which in principle is going to be set-valued. But there is one thing you can do to a continuous vector field. You can regularize. You can approximate by smooth vector fields. The flow maps of this approximating smooth vector fields will be continuous single-valued, standard dependence of the solution on the initial condition. And then it's a simple exercise. Take a continuous vector field whose flow maps are set-valued but not single-valued. Ask yourself, when you regularize, in what sense do the flow maps, the graphs of the flow maps of the regularized vector fields converge to the graph of the map of your continuous vector field? And the answer is precisely this abbreviatory sense. It doesn't converge in a better sense, like for instance, it's not true that even locally that the graphs of the approximating vector fields converge in Hausdorff measure to the limit. If you think of simple examples of continuous vector fields where you don't have uniqueness of trajectories, you'll see that when you regularize, it's not true that every trajectory of the continuous vector field is a limit of regularized trajectory. But it is true that if you have regularized trajectories staying in a compact set, you can extract a subsequence that converges to a trajectory of the limit. That is captured exactly by this particular notion of convergence. So this is one remark. The other remark is that for a number of reasons, it has turned out that this particular theory, which is one that I like because of its enormous simplicity, it's still not comparable with some other theories, like the Varga derivative containers, whose precise definition you can look up in the notes in the web page. So I have had to develop a more general theory that I call path integral generalized differentials, which seems to do everything you want to do, and in addition contains all the others. Third, for a number of reasons, one wants to differentiate not just maps defined on a neighborhood of a point, but maps defined on cones. Everything works for maps defined on cones. That's because, for example, for the Pontryagin maximum principle, when you differentiate variations, you are differentiating functions defined on an ortho. It all works except for one big technical problem, and I would like to assign that to an ambitious student. I can only prove the chain rule for path integral generalized differential on polyhedral cones. And I have a lot of trouble. I haven't been able to extend it to general cones. For the Pontryagin maximum principle, that polyhedral cones are enough, but the next item in the agenda would be to do the same thing for the Pontryagin maximum principle with state space constraints, and for there I am going to need more general cones, not necessarily polyhedral, and if by the time I get to do that, one of you can bring me the proof of the chain rule for path integral generalized differentials for general closed convex cones, not necessarily polyhedral, I will be extremely grateful and happy. Finally, I think there is a tremendous amount of room for possible generalizations of this stuff, which is fundamentally finite dimensional because it depends on variations on the theme of the Brouwer fixed point theorem, to infinite dimensions, but there, of course, the starting point will have to be a Graves open mapping theorem, which involves a stronger notion of differentiability called strict differentiability, and it would be, I think, a worthwhile task to try to figure out how to generalize, how to extend these finite dimensional theories to the infinite dimensional setting in that context. So there is a lot more work to do, and in particular to conclude. In my talk in the control session, which is going to be sometime during this week, I will discuss in detail the application of all this to proving the maximum, a very general version of the maximum principle, which is the part that I didn't want to do here because I didn't want to assume that you knew anything about optimal control. Okay, so I think I have spoken more than enough, so it's time for me to shut up. Thank you for your patience.
Time maybe for one question. If not, let me remind again that we're going to have two lectures, two sections in the special section of control, one on Wednesday, which will be even accessible for undergrad students and beyond, and one again on Friday. Is there anyone that wants to make a quick question, or we'll resume later on? Okay, so let's thank again for the speaker. And
okay. Agora não estou acreditando.